Suppose we have k independent observations of a binomial random variable x. So x here is a binomial random variable. And the little x1 to xk are k independent observations of x, capital X. So independent observations of capital X. And the question is, what are the parameters of the binomial distributed random variable x? So if we don't know what p is or what n is, how can we estimate those from these independent observations? Well, first let's start with the situation that we know n, we know the number of trials here, but we don't know the probability p of success. So if we know n and we don't know p, how do we estimate p? Well, we know that the expectation of x, expectation of a random variable, of a binomial random variable x, is n times p, the number of trials times the probability of success. And we also know that we can estimate the expectation using the average of observations. So x bar is approximately equal to the expectation of x, which is n times p. And x bar is just x1 plus x2 plus xk divided by the number of observations. So that's just the average of the observations, or the so-called sample mean, and it's an approximation of the actual mean, which is the expectation. So from this we can conclude that, well, we don't know p, what p is, but we know n, so p is approximately equal to x bar over n. So this is our estimate of p. We can just call it p hat. So this is in the case that we know n, but we don't know p. But what if we don't know both of them? Well, we can use the same idea. We can use the same idea and try to estimate both of these using higher moments. This is the first moment. We can use higher order moments of x and find estimates for both n and p. This is called the method of moments for estimation. Well, we know the expectation of x is n times p. We also know that the variance of x is n times p times 1 minus p. Well, we can also estimate the variance by the variance of observations. So this is approximately equal to the variance of observations, which is the average of observations to the power 2 minus their mean squared. This is equal to 1 over k sigma I from 1 to k xi minus their average squared. That's just the variance of the observations x1 to xk. So this is an approximation to the variance of the random variable x, which we know is n times p times 1 minus p. Now, we also know that x bar itself is an approximation of n times p. And now using this information, we can find an approximation for both n and p. We can find estimations for both of them. Well, we can simply do this. We can subtract. So first of all, this is equal to np minus np squared. Now, if we subtract this from x bar, well, x bar minus this expression here, well, I'm just calling it, let me just call this whole expression, let me just call it v, that's the variance of observations, then x bar minus v is just np minus np squared, which is np squared. On the other hand, x bar squared, the whole thing is squared, is approximately equal to np squared which is n squared p squared. Now if we divide these two, we get n. So now an estimate for n is going to be x bar squared divided by x bar minus v. This is approximately equal to n squared p squared over np squared, which is n. So now we have an estimate for n, and now that we have an estimate for n, we can use that to estimate p as before. So if I just call this estimate n hat, the estimate for n, then p hat is going to be as before x bar over n hat. So if we don't know what values p and n have, we can use our observations of the binomial random variable and find the estimate for both of them. We can estimate n using this expression, and we can estimate p using this expression.